These are the first notes in our little mini section of probability and statistics. So today involves not really probability, but getting ready to do probability. So in order to calculate the probability of an event occurring, you need to know how many total events exist. And so one of those ways is using the fundamental counting principle, or some other different techniques. So today we're just going to really concentrate on counting and totaling items. So if you would take a second and just sort of appease me here in trying this out. How many different one-topping pizzas can you create with the choice listed below? I'll go ahead and pause, noticing that you have just these options. It's a little abridged form of what the actual menu allows. But we have those flavor of crusts, and then you got to select a crust type, and then you have to select your one topping. So go ahead, pause, and then come back, and we can go over your results. So the correct answer to this is 60. And for the 60, you could get that several different ways. So I don't know who got 60 or what it was, but one of the ways that you could do that is just make a list. So some people may have butter cheese, and then R for round, and then P for pepperoni. I would just suggest, if you're going to do it this way, that you go through all the butter cheese round combinations, and then go butter cheese, deep dish, pepperoni, on and on and on. So when you make a list, that's a great way to do this. However, you just want to make sure that you do it in a systematic way so that you don't forget any, or you don't have any repeats. Because usually when that happens and you're just randomly picking things, things get lost, and it's hard to find that one last amount. Another way to do this is maybe some of you guys have what's known as a tree diagram somewhere on your paper. So you may have butter cheese, garlic herb, original, sesame, and Cajun. Those are your 5 crust flavor choices along the top. And then each of those, that's like the major branch. And then branching off of each of those is round, deep dish, thin, round, deep dish, thin, on and on and on. So each one of those 5 crust flavors had 3 different crust types. And then each of those have 4 different toppings. It could be pepperoni, ham, bacon, or mushroom, and on and on and on. And so what you'd have is all these little tiny branches. You could count up all of those branches and have 60. Because I was only asking for the total, that would be great. You could see how many butter cheese combinations you have, how many pepperoni combinations you have. You would see all the different combinations. But if you're just looking for a total, that's a lot of work. So this is where the fundamental counting principle really comes into play. If you have 5 flavored crusts and 3 crust types and 4 different toppings, you can simply multiply all of those together, and that's how you can get 60 total. You could have also done an abridged, like a little bit of just do one of these branches and then just times it by 5. So once you finished one whole butter cheese tree diagram, you'd realize there were 12 choices for butter cheese. Well, then that means there would be 12 choices for each flavored crust. 12 times 5 is 62. 60 as well. So just going into this, some vocab. I'm going to let you guys maybe get a good time to pause here. It is not 12.1. I know that's an old book, but the vocabulary terms here are important to understand. So if you guys could just write those down, maybe pause here, get them all written down, and then we'll go over them on the next slide. So in reference to the Hungry Howie's warm-up, the vocabulary being explained, all the possible pizza combinations would be an example of our sample space. Obviously, Jets would have a different sample space, or maybe if we included all the different varieties of crusts and toppings, it would be even a bigger sample space. When we talk about a garlic herb, thin crust pepperoni pizza, that would be an example of an outcome. It's just one of the one-topping pizzas that were available. The actual act of choosing or selecting a pizza with a deep dish crust would be an example of an event. It's what's occurring, with the thing that's happening. Does the flavor crust affect what topping I can choose for my pizza? I mean, other than personal choice, no, it really doesn't. You could make any combination. Some might be gross, personally speaking, in your opinion, but we don't take opinion into consideration. So once we answer no there, then so choosing a flavor of a crust and choosing a topping are what we could call independent events. It's just important to note that they're separate from each other, so the one is not going to affect the other. So if that's independent, let me just give you an example of dependent. A lot of times in probability, we love to use a deck of cards. So if I drew a card from my deck of cards and I laid it down, not replacing that card in the deck of 52 cards, I'd only have 51. And I'd only have one less. If that card was a king, I would have one less king, I'd have one less maybe heart, and I'd have one less card total. So all of those things could depend on the probability of the next event happening if I don't replace it. So a lot of times they'll talk about replacing or not replacing. That's really the difference there. Here's the fundamental counting principle that I described where you just multiply. So if you have the event M, can happen M ways. Event N can happen N ways. You know, your event M would be crust flavor. There were 5. And then event N would be crust type. There were 3. And then we had even more than that. We said the topping choices. So you just multiply them, all the choices together, and that's what works. It works both with independent and dependent, but like I said, dependent, you have to kind of manipulate the data a little bit more because maybe there's not as many choices. It works with 2 or more events because you have to have at least 2 things to use multiplication. So let's just try a few. So a sandwich menu offers customers a choice of white, wheat, or rye bread with 1 spread chosen from butter, mustard, or mayonnaise. So you have 1 bread, 1 spread, and 1 meat chosen from turkey, ham, or roast beef. How many different combinations are possible? So one of the ways we write this is we kind of use like some brackets and we say, what are we talking about here? We have bread choices. And then that's one of the events, selecting the bread, the spread, what we're going to put on the bread, and then the meat choice. By just kind of organizing our thoughts in that format, now we can go back and say, well, there were 3 choices of breads, and there were 3 choices, butter, mustard, and mayo for our spreads, and I believe there were 3 meats, turkey, ham, and roast beef. And so we ended up with 27 total different sandwiches that had 1 type of bread, 1 type of spread, and 1 type of meat. This one's going to be your practice problem. I'm not going to write that down. I'm just going to check your notes when I come back and hope that you guys listened to these notes. But you're going to come up with a situation where there's 24 total possibilities. I don't care how many events you create. You got to have at least 2, totaling 24. So come up with a story. Maybe you're a different sandwich shop, a different pizza, outfits when you're packing a bag. How many outfits can I come up with different clothing pieces? All sorts of things we can do here. So I will check that upon return. So this is where they're not listing everything out like in the sandwich shop, but this is where that little organization of what they're asking us kind of helps us solve the problem. How many 4-digit cell phone voicemail codes are possible? So when you talk about a 4-digit code, I guess there's not different categories. We are just looking at 4 different digits, 4-digit cell phone voicemails. So I sometimes, there's not different categories that we're looking at. We're just looking at numbers, but the number system, I have digits 0 through 9 that can go here, 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 and here. Didn't say anything about not repeating. I could have a 0000 voicemail code. I could have a 1111, but that's where maybe they would tell us that they couldn't repeat or you can't have a number here. So those are dependent. This one would be independent. So out of 0 through 9, that is 10 digits, times 10 more digits for that one, times 10 more digits for that one, and times 10 for that one. So we end up with a total of 10,000 different codes. So you'd have to try 10,000 different combinations before you cracked the code. You can see how that's just a 4-digit code on a voicemail, but most passwords now are like 8 different letters and characters and such. So they get lots and lots of passwords available. Okay, so now this one's talking about a license plate. Some states require the use of 3 letters and 3 numbers on their license plate. So that would look like this. We've got numbers and letters, but technically we have 3 of each of those, right? 3 numbers, 3 letters. Determine the number of possible license plates for the state. They didn't mention that nothing can repeat. There's no numbers or letters that aren't allowed to be used. And really, when we multiply these things, our choices, order doesn't matter. So I might just say number, 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 alpha, 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 or letter, letter, letter. There are 10 digits that can go here, 10 here, 10 choices here. Again, some states, they might say you can't have 0 in the beginning. I don't know why they would. Just like phone numbers, you really can't start with a 1 because 1 is the denoted number for long distance. There are 26 letters in the alphabet. Didn't say anything that they couldn't repeat. And so all of them are 26 there. And so when you're all said and done, you got 10 times 10 times 10. Times 26 times 26 times 26, this gigantic number, 175,760,000. So there are 17,576,000 license plates with 3 letters and 3 number combinations. And it doesn't mean that the 3 numbers have to be out in front. So if I rearranged any of these, I'd still get that same amount. How many different phone numbers does Marine City have, assuming they begin with 765? So 765, I believe Marine City has another 3-digit number, but that tells us Marine City. Then there are 4 digits that follow. There's no rhyme or reason. You could have repeat. Again, so this is independent. So there are 10,000 phone numbers for 765. Now, as communities grow, fax numbers, there could be fax numbers with 765. They had to sometimes they have to come up with a different 3-digit number to represent that city because we run out of phone numbers. I don't think that's a problem with landlines anymore with the introduction to cell phones. Okay, my friend's phone number ends in the digits 1, 2, 3, 4. Okay, so now I know it has these digits, but I'm not sure the right order. How many total phone calls would I have to make to get the correct phone number? So we're talking about the last 4 digits again. So maybe it is that order, 1, 2, 3, 4, but this is a little bit, this is dependent, and it's dependent because I know that those 4 exist. So this first one could be 1, 2, 3, or 4, right? So there's 4 choices. But once I select, I don't care which one it is. If it's 1, then 1 can't be in these other spots. So there's only 3 more choices, right? If it was 4, then it can't be 4 and it has to be somewhere else. So each subsequent number digit has less choices that it can be. All the way down to the bottom, the very last one, where, hey, if I know, for instance, maybe that's the number, 4321. But as soon as I lock in 4 here, 4 can't be anywhere else. So it's 1 less number. Right? Once I lock in a number here, it can't be anywhere else, and neither can the first one, so that's 2 less numbers, so I only have 2 choices. So when I multiply this, 4 times 3 times 2 times 1, 24. I'd have to make 24 phone calls, and after that, as long as I didn't repeat them. Now that's where, if I'm going to do the phone calls, I would actually have to list all the phone numbers, and that's where a list or a tree diagram comes into play. If you have to know, okay, well, what numbers should I dial? If this is 1, then this could be 2, 3, 4. If this is 2, this could be 1, 3, 4, and on and on and on. 1, 2, 3, 4. And so then I could just dial 1, 2, this one would be 4, this one would be 3, right? So I could dial this, I could dial this, and then I just keep track. So you'd have to know all of them. So sometimes they ask you to list. 24 is not too big to list, but some of these numbers, like 10,000 of them, it would take forever to list all those choices. How many different passwords can I create based on the following criteria? Has to be 6 characters long. So I got my 6 characters. Must begin with a 1-digit number. I don't know the other 6 characters the other 5 characters must be lowercase letters, but no repeats. Okay, so but no repeats means once I use a letter, I can't use it again. And the fact that they mention lowercase, unless they talk about case, we usually use 26 letters. If they said lowercase and uppercase, well, that's 52 because you got double the amount of letters. All right, so the first one has to be, so this is kind of what we're looking at here. We're looking at a number. And then 5 letters, and just making a note that they can't repeat. Didn't say anything about what the number it could be, so I know I have 10 choices for my number. Sometimes I just make my little symbols like this. Sometimes this helps. We're going to use that later on in probability, so just getting used to that format. I also sometimes like put a little star next to this saying, hey, after that first one, it's dependent, so I need to make sure I'm taking that in consideration. So for this first alpha, I had 26 choices, but once that letter is there, I don't care what letter it is, that letter is no longer in circulation to be chosen because we can't repeat. So then I have 25, 24, 23, and 22 options. And when I calculate that, I end up with 789,360,000. 78,936,000 different passwords. And notice passwords have changed. There's so many passwords in circulation, and they're trying to make it harder to guess. So sometimes they even have criteria where it can't go in a row, 1, 2, 3. It can't repeat. You got to have a symbol, all sorts of things. You have to have one capital, lowercase, all different criteria. List all the possible ways to flip a coin. Man, lots of problems here spelling. And roll a dice, 6-sided dice. Okay, so it's asking us to list. I do know, though, if I'm talking about flipping a coin and rolling a die, okay, using the counting principle, I at least know how many will be in my list. So when I flip a coin, I got 2 options. I got a heads or a tails. And when I roll a dice, I have 6 options. I can roll 1, 2, 3, 4, 5, 6. So I need to list a total of 12. If they just said come up with the number, I would put 12. But because they actually said specifically to list, I'm going to go ahead and list them. I can list them in 2 different ways. I can say I rolled heads and I got a 1. Go through all your head combinations. And then go through all your tail combinations, tails 1, tails 2, tails 3, tails 4, tails 5, tails 6. Okay, another way to do the same thing is just come up with your tree diagram. So I have heads here and I have tails here. Heads could get a 1, a 2, a 3, a 4, a 5, a 6. And tails could get a 1, a 2, a 3, a 4, a 5, or a 6. This technically isn't a list. This is a list. Sometimes this helps us get to the list. So just technically speaking, that's a tree diagram, that's a list. But the tree diagram could help us create the list. All right, so you're going to have a worksheet. Majority of them on the worksheet, you're going to use the counting principle. I showed you some different techniques. However, there's a couple where the counting principle just doesn't work. So you're just going to have to think cleverly and come up with a different way to count the total. Remember, we're looking for the total amount of something. So I bold printed those so you knew which ones they were. And I think there's like one where you would actually have to list out the results. But majority of it is counting principle. Some is independent, some is dependent. Good luck.